Assalamualaikum warahmatullahi wabarakatuh. Thank you very much for the time. Let me introduce myself first. My name is Reni. This is our joint research, me and my friend Ilham Saifuddin. The title is Determination of Bullock Regional Subdivision in East Java using Connected Domination Number Theory. I will show the introduction, result, conclusion, and references that which be used in this research. Bullock is a state-owned public company engaged in food logistics. There are about 18 Bullock warehouses in East Java province with an uneven distribution because the scope of Bullock's business includes logistics or warehousing, service and pest eradication, provision or plastics bags transportation business, food commodity trading and retail business. There must be good coordination between regional subdivision and warehouse complexes. In this study, the minimum regional subdivision recommendation in the East Java region were determined using the theory of connected domination number in graphs. The location of the warehouse complex is described as a vertex and adjacent warehouse complexes are connected by edge. In this research, we also determined the connected domination number of vertex and edge amalgamation operation for several classes of graphs. This is some definition. First definition. Let G be a graph with vertex set V and edge set E. Let S be the subset of vertex set V if every vertex in V without S is adjacent to minimum one vertex of S, then S is said to be a dominating set. And then for the second, the size of a smallest dominating set is referred as dominating number of a graph G denoted by gamma G. Where for the next, it is the definition of connected dominating number. A dominating set D is said to be connected dominating set if the induced subgraph D is connected. The connected domination number denoted by gamma CG is the minimum cardinality of a connected dominating set. This is the figure, the example of a graph with connected dominating set. The vertex element of dominating set here is given by green circle here, and it was connected each other. And then some result before here. Dominating connected dominating number of complete graph is equals 1, and then connected dominating number of bipartite graph is equals 1 if m equal 1 or n equals 1. It was equals 2 for m n more than equals 2, and then connected dominating number of cycle is equals n min 2 n minus 2. Sorry, I think I forgot to give equal sign. And then connected dominating number of path is equals n minus 2, and then this is for the lower and upper bound of connected dominating number based on the based on the cardinality of the vertex set and edge set, and also the maximum degree. Because we will show some connected dominating number of graph amalgamation operation, especially for vertex amalgamation. So here I give the definition of vertex amalgamation. Let G1, G2 until GT are subgraph of G and V element of V. If G equals to union I equals 1 until T of Gi, and the intersection of Gi for I equals 1 until T, it is equals V, vertex V, then G is a vertex amalgamation of G1, G2 until GT at vertex V, denoted by like this. If G1, G2 until GT has N1, N2 until NT vertices respectively, then then the graph vertex amalgamation has N1 minus T plus 1 vertices. Okay, this is the result, the first result. We operate the sum classes of graph. They are cycles, path, star, and complete bipartite. Here, let G equals to vertex amalgamation V of Cn, Pm, Sk, and Bx, y is amalgamation vertex of cycle, path, star, and complete bipartite graph with the edge order is n more than equals 3, m more than equal 2, k more than equals 3, and x, y more than equals 2. Then connected dominating number of G is equals n plus m minus 2 if V of Sk is one of the pendant and V of Pm is V1 or Vm. And then it is equals to n plus m minus 3 if V of Sk is one of the pendant and V of Pm is Vi for I more than equals 2 and less than equals n minus 1. So here I give the illustration of the figure Cn, Pm, Sk, and Bx, y if we do the vertex amalgamation to these graphs. This is the cycles, and then this is the path, this is star graph, and this is the complete bipartite, and then this vertex is V, vertex amalgamation. The second possibilities, if the V of Pn is not equals the leaf or the pendant of the path, so it can be the second vertex, maybe the third, until like this, maybe the middle of the path here. So based on the theorem, we get the value is n plus m minus 3. Another result is if the difference with the theorem before is for the V of star graph, we take the center of the star. So the figure is like here. The result are also give two case. It equals to n plus m minus 3 if V of Sk is a vertex with order n minus 1. V of Pm is V1 or Vm, and then it is equal n plus m minus 4 if V of Sk is a vertex with order n minus 1, sorry, it is k minus 1, and then phi of Pm is phi I for I more than equals to less than equals n minus 1. This is another possibility of of another figure. And then for the case 2D, we use the theory to get the connect dominating number of BU graph. Here I give the name of this graph is BU graph. BU graph is representation of map of block office in SJava, and then I write this map become this graph, BU graph, and then based on the theory of connected dominating number, we get the gamma c, this is gamma c is equals 8. So in this paper we can determine the connected dominating number of some vertex amalgamation graph, which consisting of cycle, path, start, and complete bipartite graph with some possibilities for the position of the center vertex amalgamation. By applying the theory, we also can determine the number of block regional subdivision in SJava. From 18 location, we get 9 location can be recommended as block regional subdivision to dominate all location. We also give the open problem: find the connected domination number for another particular classes of graphs, and the graphs obtained from graph operations such as edge amalgamation, join, or cycle operation. This is the references that we used. Thank you very much for the attention. Assalamualaikum warahmatullahi wabarakatuh.